biggest ambitions. The search for a unified understanding of everything.
It's a quest that goes way back. Right. From Newton seeing the same force pulling apples and holding planets.
Exactly, to the standard model weaving together the fundamental forces we know. Progress often, that's the one, a quantum vibrational universe. The idea is that everything, an object's properties, even its place in space-time, stems from underlying vibrations.
And gravity, how does that fit in?
Well, in this picture, gravity isn't quite a force. It's described as a spherical vibrational emanation from one object that changes the path of another, makes it fall inwards.
Huh. It sounds appealingly simple, almost intuitive.
It does, doesn't it? But our mission today is to take this intuitive idea and really scrutinize it using the tools of theoretical physics.
Right. We need to see how it stacks up against the heavyweights general relativity quantum field theory.
And crucially, does it match the observations? All that data we've gathered that forms the bedrock of modern physics.
So we'll be unpacking the concepts, looking at some maybe surprising historical context.
Yep, and confronting what this theory implies about matter, space-time, and gravity itself. So let's dive in.
Okay.
So this core idea, everything is vibration. What does vibration actually mean in physics terms? How do physicists formalize that?
Well, it's interesting because the idea of an object's nature being vibration actually has a pretty direct parallel in quantum field theory, QFT.
Okay, QFT.
Yeah. In QFT, particles like electrons or photons, they are really minuscule billiard balls.
Right, they're excitations in fields.
Exactly. They're quantized excitations. You can think of them as localized ripples or, well, vibrations in fundamental fields that permeate all of space.
And
the energy of a particle. That just corresponds to the amplitude, the strength of that vibration.
so the basic concept of vibration isn't completely alien to how we already think about fundamental physics?
Not at all. It maps quite well onto that aspect of QFT.
Okay, so the theory talks about these spherical emanations from massive objects influencing others. How does physics classify that kind of influence? Because fields come in different types, right?
You're absolutely right. Physics has a clear way to classify these things based on what kind of information the field assigns to each point in space.
Like temperature, maybe.
That's a perfect example of a scalar field, rank 0. It assigns just a single number, a magnitude, no direction to every point. Temperature in this room, pressure, the Higgs field. Those are scalars.
Okay, just a value everywhere.
Then you have vector fields, rank 1. They assign both a magnitude and a direction. Think wind velocity or an electric field pushing charges around.
Push and pull.
And then you get more complex things. Tensor fields, rank 2 or higher. They describe properties with multiple directions, like stress in a material, or crucially, the metric tensor in general relativity, which describes space-time geometry.
So back to the theory's spherical emanation from a central point of maximal harmony, where does that fit?
That description fits a scalar field perfectly. Imagine a single point source emitting something uniformly in all directions.
Like ripples on a pond spreading out.
Kind of, but without a direction of flow, just an intensity value. A static point source in a scalar field naturally creates concentric spheres, where the field value is the same everywhere on a given sphere. That's isotropy, same in all directions. And harmony suggests a single state or magnitude.
So it's a scalar field.
That's the most direct interpretation.
So for our analysis, let's call this fundamental field the harmony field, symbol ALA, and treat it as a scalar field mediating gravity.
Okay, here's where my history bells start ringing. A scalar theory of gravity.
Mm-hmm.
That sounds familiar. Hasn't this been tried before?
You are spot on. This isn't a brand new concept in principle. Back in the early 20th century, people like Gunnar Nordstrom developed mathematically sound scalar theories of gravity.
Really? Before Einstein finalized GR?
Yes, and they were simpler in many ways. They were serious contenders for a while.
So what happened? Why aren't we using Nordstrom's theory today? The crucial test came down to how gravity affects light. Gravitational lensing.
The bending of starlight near the sun.
Precisely. Newtonian gravity, treating light sort of like a very fast particle, predicted a certain amount of bending.
Okay.
These pure scalar theories, like Nordstrom's, they predicted zero deflection. None at all.
Zero. Why zero? That seems counterintuitive if it's a theory of gravity.
It's because of how scalar fields couple to things. In those simple models, they coupled primarily to mass. Photons are massless, so the scalar gravity field essentially didn't interact with them. It couldn't bend their path.
Okay, so scalar theory said no bending. What did Einstein predict?
General relativity, Einstein's tensor theory, predicted a deflection exactly twice the old Newtonian value.
Twice. Why double?
Because in GR, gravity isn't a force between masses in flat space, it is the curvature of spacetime itself. Light, like everything else, travels along the straightest possible path, a geodesic, through this curved spacetime. Both space and time curvature contribute, leading to double the Newtonian effect.
And then came Eddington's eclipse expedition in 1919.
Exactly. Eddington and his teams observed starlight bending around the sun during a total solar eclipse, and the measurements matched Einstein's prediction, not Newton's, and certainly not the zero prediction of scalar theories.
Wow. So that observation basically killed pure scalar gravity theories right there.
Pretty much, yes. It was a decisive blow. So what does this history tell us about our harmony field theory?
It can't be just a scalar field doing the job of gravity.
Precisely. For this vibrational theory to even stay in the game, it has to be what we call a Scalar-Tensor theory. The harmony field can't replace space-time geometry. It has to interact with it, maybe modify it. It needs that geometric part, the tensor part, to get light bending right.
That's a fundamental constraint right from the start. It can't just be a ghost.
Non-negotiable. Otherwise, it's ruled out by observations made over a century ago.
Okay, let's talk quanta. If the harmony field is scalar, what kind of particle is associated with it?
Right, so in QFT, the type of field determines the spin of its quantum particle.
Spin, like intrinsic angular momentum.
Sort of, yeah. A scalar field, rank 0, corresponds to a spin 0 particle. A scalar boson. The Higgs boson is the famous example.
Okay. And other fields?
A vector field, rank 1, gives you a spin 1 particle. A vector boson, like the photon for electromagnetism. And crucially, a rank 2 tensor field, like the metric tensor in GR.
That implies a spin 2 particle.
Exactly. The hypothetical graviton, the quantum of gravity in GR, must be spin 2.
So our harmony field, being scalar, would mean gravity is mediated by a massless spin 0 boson.
That's the implication. And that's fundamentally different from GR's spin 2 graviton.
How different? What does the spin actually change?
The spin dictates the nature of the force. Spin 0 particles, spin 1 and spin 2 medium forces with different characteristics, different ways they couple to matter and energy. As we saw with light deflection, a pure spin 0 mediator interacts differently than a spin 2 mediator. It's a core change to gravity's identity at the quantum level.
Okay, let's shift gears slightly to the theory's grander ambition, unification. It claims all elementary particles are just different vibration patterns of this single harmony field.
Yeah, it's a very elegant, very parsimonious idea on the surface. One field to rule them all.
Sounds great. Too great.
Well, it hits a massive wall almost immediately, a really fundamental one in quantum physics, the spin statistics theorem.
Okay, what's that?
The standard model, our incredibly successful theory of particles, has lots of different quantum fields. Broadly, you have fermions and bosons.
Fermions are matter particles, right? Electrons, quarks.
Exactly. They have spin 12. And crucially, they obey the Pauli exclusion principle. No two identical fermions can be in the same quantum state. This is why matter is stable, why atoms have structure, why you can't walk through walls.
They take up space.
In a quantum sense, yes. Then you have bosons as force carriers like photons, W and Z bosons, gluons, and the Higgs. They have integer spin, 0 or 1. They don't obey Pauli exclusion. You can pile many bosons into the same state, like photons in a laser beam.
So fermions are like the bricks, bosons are like the mortar, and maybe the message is passed between bricks.
That's a decent analogy. Now,
Sure.
Here's the problem for the vibrational theory. How can one single scalar field, which naturally produces spin 0 boson excitations,
How can it also produce spin 12 fermion excitations that obey the Pauli principle?
precisely? There's simply no known consistent way within quantum field theory for a fundamental scalar field to give rise to particles with half-integer spin that behave like fermions. It's like trying to get matter with structure out of something that fundamentally likes to clump together.
So you can't just vibrate a scalar field and get an electron out?
Not in any way that physics currently understands. It violates fundamental connections between spin and particle behavior, and there's more.
Oh.
The standard model isn't just a list of particles. It has a very specific mathematical structure, a gauge symmetry group, U1, SU2, and C3, that dictates all the forces and interactions.
The rules of the game.
Exactly. This vibrational theory offers no mechanism, no explanation for where this complex and precise symmetry structure comes from if everything is just vibrations of one scalar field. It's a huge explanatory gap.
Okay, that sounds like a major theoretical stumbling block.
It's arguably the biggest one, yeah.
Let's pivot to spacetime then. The theory says closeness of vibration corresponds to closeness in spacetime. That implies spacetime isn't the basic stage, but something that emerges from the harmony field.
It does. It flips the script. Usually we think of fields existing in spacetime. Here, spacetime is the field, or at least determined by it.
How would that work mathematically?
Well, formally, the metric tensor, G, which is spacetime geometry, would have to be some function of the harmony field. So mean phi pic.
What's the simplest version of that?
The simplest would be if spacetime was conformally flat. That means the geometry is just flat Minkowski spacetime, like in special relativity, but stretched or shrunk by a factor that depends on the harmony field everywhere. So Geim domain.
Okay, but wait. If the harmony field defines space-time, what space does the harmony field itself live in? Doesn't that just push the question back?
Huh. Yes, it creates a potential circularity. And the way out is usually to postulate some kind of pre-geometric substratum.
Pre-geometric, meaning before geometry even exists.
Exactly. A more fundamental layer of reality. Maybe it's just abstract mathematical relationships, a network of connections, something discrete from which our familiar smooth spacetime emerges as a large-scale property of the harmony field's configuration.
Wow. That actually sounds like some ideas in quantum gravity research, where space-time is also thought to be emergent.
It does align with those cutting-edge themes, yes. It suggests spacetime isn't the final word.
Now, one thing the theory seems to capture quite nicely is the geometric picture of gravity from GR. You mentioned objects follow geodesics.
It does that part very elegantly. Just like in general relativity, things don't feel a force of gravity in this theory.
They just follow the straightest path.
They follow the straightest possible path, the geodesic, through whatever geometry they find themselves in.
So how does the harmony field create that geometry?
A massive object in this theory is just a large, stable excitation of the harmony field. This creates a significant variation in the field around it, that spherical emanation.
A gradient in A.
Right. And because the spacetime metric again depends on A, this gradient in A means the affected metric changes from place to place. Spacetime becomes curved.
Ah, so the curvature isn't fundamental, but it's induced by the harmony field's shape.
Precisely. Other particles moving nearby just naturally follow their geodesics through this curved geometry dictated by A. The altered trajectory, the falling inwards, is simply the particle tracing the straightest path available in that environment.
So it reproduces that core geometric insight of GR, but derives it from the scalar field.
That's the idea. Conceptually, it's quite neat.
Okay, but concepts need to face reality. We need to talk about observational tests. You mentioned the pincer movement. Any new theory has to match GR's successes and hopefully fix its problems.
And GR has had a lot of successes, tested to incredible precision.
Let's go back to gravitational lensing. We know a pure scalar theory fails. What about the required Scalar-Tensor version?
A Scalar-Tensor theory can be made to work, to give the correct light deflection, but
There's always a but.
there's usually a but. It often requires carefully choosing or fine-tuning the specific mathematical functions that describe how the scalar field couples to geometry and matter. You have to fiddle with the parameters to get the right answer.
Whereas GR.
General relativity predicts the correct deflection angle with no free parameters related to the bending itself. Its prediction comes straight from the core equations. And current measurements confirm GR's value to about 0.04% precision. Any scalar-tensor theory has to match that, often making it seem less predictive, more engineered.
That's a very high bar. What about gravitational waves? LIGO, Virgo, Chiara. These seem like the ultimate test beds now.
They are absolutely crucial. And the vibrational theory, even in its scalar-tensor form, faces huge challenges here. Two main ones.
Okay, what's the first?
Polarization. How the wave stretches and squeezes space. GR's spin-2 graviton produces tensor waves. These have two distinct ways they can deform space, called plus-plus and cross-egg polarizations.
Like stretching horizontally, then vertically, or diagonally?
Sort of, yes. A fundamental scalar field, being spin 0, would produce scalar waves. These only have one polarization mode, a breathing mode, where space expands and contracts uniformly in all directions spherically.
So GR predicts two modes, scalar predicts one breathing mode. What do we see?
All the gravitational waves detected so far are perfectly consistent with GR's tensor polarizations. There's no sign, no evidence whatsoever of a scalar breathing mode component.
So if the harmony field exists and contributes to gravity, its waves should be showing up, but they aren't.
Exactly. A scalar tensor theory would generally predict a mixture of scalar and tensor waves. The fact that we only see the tensor kind puts very tight limits on how strongly any scalar field, like our harmony field, could be interacting gravitationally.
That sounds good for the theory. What's the second challenge?
Speed. The speed of gravitational waves. This one is maybe even more constraining.
Ah, I remember the neutron-star merger.
GW 170817.
Yeah.
August 17th, 2017. We detected gravitational waves from two merging neutron stars, and just 1.7 seconds later, space telescopes detected a gamma ray burst from the same event.
After traveling for how long?
About 130 million years. For light, the gamma rays, and gravity waves to arrive almost simultaneously after such a colossal journey means they must travel at exactly the same speed, the speed of light.
So incredible precision.
To 1 part in 10 to the 15. That single measurement wiped out huge swaths of alternative gravity theories overnight.
Why? Don't most theories predict gravity travels at sea?
GR does. But many modified theories, especially many scalar-tensor theories, naturally predict that the gravitational waves, or at least the scalar part of them, might travel at a slightly different speed than light.
And GW 170817 said nope.
Pretty much. For this vibrational theory to survive, any gravitational waves it produces scalar or tensor components must propagate at precisely c. This is a very strong, non-trivial constraint on the structure of the theory. Many simple scalar tensor models just don't satisfy it naturally.
So lensing is tough, polarization is missing, speed is incredibly constrained. What about black holes? Do they look different in this theory?
They could, yes. In GR, black holes are famously simple. The no-hair theorems say they're defined only by mass, charge, and spin. All of their details are lost.
Like cosmic baldness.
Exactly. But in scalar tensor theories, black holes can potentially have scalar hair.
Meaning they carry an imprint of the scalar field?
Yes, so they can have an external scalar charge associated with the harmony field. This would mean the gravitational field around them isn't just determined by mass, charge, and spin, but also by this scalar hair. Their properties could be different.
Okay, that sounds like something we could potentially test.
We can look for subtle deviations. For instance, in the orbits of stars whipping around supermassive black holes, like the star S2 orbiting Sagittarius A in our galactic center, if there's scalar hair, the orbit might differ slightly from the GR prediction.
Precision measurements.
Extremely precise ones. Or we could look at the shadow of a black hole, the silhouette imaged by the Event Horizon Telescope. Scalar hair could potentially alter the size or shape of that shadow compared to GR.
So these are direct probes for the harmony field's effects in the strongest gravity regimes.
Exactly. They offer a window into testing these modifications.
So if someone wanted to make this theory truly quantitative, truly testable, what's the path forward? What math needs doing?
Well, first, you need to write down a specific mathematical rulebook for it, a Lagrangian density. This equation basically defines how the harmony field A behaves, how it interacts with itself, with matter, and with the space-time metric band.
And where would that fit in the landscape of theories?
It would almost certainly fall into a known category of modified gravity, likely a generalized Brans-Dicke theory, or maybe something called FR gravity, where R relates to curvature and LA are scalar field. These frameworks already exist.
So the task is finding the right version within those frameworks.
Exactly. You need to find specific mathematical forms for the various functions and potentials in the Lagrangian, and the goal would be twofold.
1, pass all the tests we've talked about.
Yes. Light deflection, gravitational wave speed and polarization, solar system tests, black hole observations. It has to reproduce all of GR's successes in the regimes where GR is tested.
And 2,
Hopefully it offers something new. Maybe it can explain dark energy or drive cosmic inflation in the early universe, things GR struggles with. It needs to solve a problem GR can't while matching everything GR gets right.
that sounds incredibly difficult.
It is, and we haven't even fully circled back to the biggest issue.
The matter problem, getting electrons and quarks from vibrating.
That remains the Everest to climb. As we discussed, generating the whole particle zoo of the Standard Model, especially the fermions with their specific spin and statistics, and the intricate symmetries U1, XSU, 2, XSU, all from a single, simple scalar field. There's just no known theoretical path to do that. It seems fundamentally impossible with current physics.
So let's summarize the comparison. Standard model plus GR versus this vibrational universe idea. Key differences.
Okay. Source of gravity. GR says space-time curvature. Vibrational theory says the harmony field determines geometry.
Mediating quantum. GR predicts the spin-2 graviton. Vibrational theory implies a spin-0 scalar boson, at least fundamentally.
Nature of space-time. Fundamental stage in GR, emergent property of the harmony field in the vibrational theory.
Nature of matter. In the Standard Model, fundamental excitations of many distinct fields. Vibrational theory hopes for modes of a single harmony field, but faces huge hurdles.
Right, gravitational waves. GR has transverse tensor waves, plus cross. Vibrational theory fundamentally has scalar waves, breathing mode, plus potential tensor parts in a scalar tensor version, but the scalar part seems missing observationally.
Fundamental symmetries. Precisely defined in the Standard Model. U1 XSU XU3. Vibrational theory needs to explain or derive these, which is a major challenge.
That covers the main contrasts.
So wrapping up this deep dive, this quantum vibrational universe idea, it's conceptually quite rich, even beautiful in its simplicity.
It is. And when you formalize it, parts of it resonate with established physics, like particles as field excitations, gravity as geometry via geodesics.
Interpreting it as a scalar tensor theory where this harmony field shapes space-time seems the only way forward theoretically.
But then it slams into the wall of observation and theoretical consistency.
Right. In its simplest, pure scalar form, it failed over 100 years ago with light deflection.
To survive even notionally, it needs to be a finely tuned scalar tensor model that somehow mimics GR perfectly where tested.
And the biggest hurdles remain. Matching the observed gravitational wave properties, their speed matching light, the lack of scalar polarization.
And the Mount Everest.
Yeah.
Somehow generating the entire standard model, especially fermions and the known forces, from just one scalar field. There's currently no known physics that allows for that.
So bottom line assessment on viability.
In its present conceptual form, and given the known constraints and lack of a mechanism for matter generation, it's just not a viable competitor to the standard model plus general relativity.
Okay. Not viable currently.
Not really, no.
But even if it doesn't work out, exploring ideas like this has value, right?
Absolutely. It's a fantastic exercise in foundational thinking. It pushes us to re-examine why we believe what we believe about gravity, matter, space-time. It forces us to confront the assumptions baked into our current theories.
And it really underscores just how rigorously tested and successful GR and the standard model actually are. Any alternative has an incredibly high standard to meet.
Precisely. It highlights the power and the burden of observational evidence in physics. Intuition is vital, but data is king.
So a final thought for you, our listener, to ponder. If our universe were fundamentally vibrational, if space-time really does emerge from an underlying harmony field, what deeper score or rhythm might be dictating those vibrations, and what kind of instruments, what kind of physics would we even need to perceive that more fundamental pre-geometric reality?